So we'll start the second lecture of today. It's by D. Jogic from ISI Bangalore, who's going to talk about limit theory for spatial interacting systems.
Thanks, Pierre. Thanks, Riddhi and Anirban for inviting me and re-inviting me. And also, it's nice to follow up with Shubhro. There'll be a few things I'll refer to Shubhro's talk. So this is a joint work with my two collaborators, none of whom are here. So some questions I will defer it to rather Shubhro. Okay. Okay, so I'll give a brief the outline. I'll divide it into 4 parts, and I hope to somehow make some things in each of the 4 parts accessible independently. And so I'll just briefly explain the framework in a couple of slides and then give examples to illustrate what kind of theorems, what kind of models are we looking at, and then give an overview of the general theorem with very brief some words about the proof. And then important concept for us is a notion of a localization or stabilization, which allows us quite a bit to do, is what I call it bounded Lipschitz or BL. And before going, as I said, as I put the slides, you can download it, and in case at some time you are bored, you are free to access that also. Okay. So let's start with some basic point process notions, and you will see there's some overlap with some of the talks earlier. So for me, a point process, we'll be talking only about Euclidean point process in D dimensions. Is a set of random points in RD, or I will also think of it as a random locally finite counting measure. Okay, so sometimes the measure theoretic notion, sometimes the set theoretic notion, notation, both are helpful for us. Okay, so this is a point process, a collection of random points or a collection of random Dirac masses. And I will assume stationarity. At some point, stationarity is not important, but nevertheless, I'll assume stationarity. And so it means that whenever I shift my point process by some y, any y, it is invariant under the distribution is invariant under any shift. Okay. Some examples. So Poisson point process, which all of us have seen, as most of us have seen for sure, is that if I restrict to any bounded set, the number of points is a Poisson distributed with the Lebesgue volume. Mod A denotes the Lebesgue volume and distributed uniformly. A Genebre point process, again, we have seen. So in Shubhro's talk, there was alpha determinantal. One of the Genebre is a 2, alpha equal to 1, and you can see or -1. And this comes as a limit. In a way, you can think of it as a limit of eigenvalues of a n cross n matrix with n going to infinity. And so here is a representative figure. Is a Poisson point process, a Genebre. And this is a Cox point process. Some of you would have seen it in Benedict's lecture in last week. So it shows that point process can be in different ways. This is completely independent. Poisson is a very independent point process. Genebre has some repulsive structure, and Cox has a clustering structure, some attraction. Okay, so it's quite possible we deal with any of these models, but I'll be less precise on the precise. But you can take, for example, any of these 3, like Poisson and Genebre are 2 things you can keep in mind throughout. Okay, if nothing else, even for Poisson there are some new things, so you can keep Poisson and Genebre in mind. And a third notion I will need is what is called a Mach point process. That is, to each of the points of the point process, I'll attach a label. So this label, I will allow it to be in a Polish space. For most of the talk, I'll be using only R itself, very simply, but it's of good to think that we can actually allow Polish space. Okay, so it means that again a point xi in RD and mi in M, such that if you restrict to the first coordinate, it's a point process. That is, these are all distinct points. Okay, the first coordinates, it's all distinct points. Okay, so each point gets a label or a mark. This is what we call a Mach point process. Okay, so here is our framework. So we will assume a stationary point process to begin with, for example, a Poisson or Genebre. And the key property of both that allows us to do is what is called asymptotically decorrelated. I will make this precise in the later half of the talk, what is asymptotically decorrelated for us. So I'll make this notion more precise later. Then we have a graph. On this point process, I'm going to define a graph. How is the graph defined? Is that I take my set of points to be the vertex set, and I have a translation invariant. I call it quasi-local. I'll make it a little more later clear, but is some kind of local rule for putting edges in a translation invariant manner. For example, just fix this for the talk, that's quite good enough, is that we can take a k nearest neighbor graph. That is, x and y are connected if x is the k nearest point to y or vice versa. So you put a rule for putting edges, one of the two conditions is satisfied. Either y is the k nearest point of x or x is the k nearest point of y. This is clearly translation invariant, okay, doesn't, because you're just measuring relative distances. And it's quite possible you may have long edges. For example, if I take red point to be my x, red is my x, then it can get connected to these 3 points y, okay? These 3 points y and maybe even some more. These are the 3 nearest points to the red point, the 3 magenta. But if I take k to be 6, I get 3 more points, okay? So there are totally 6 nearest points, and then, okay, some more may have no thing, it will get connected. And, okay. So if a very simple case, if I take k equal to 1 and 100 sort of 100 points, maybe, I got it truncated badly, maybe I think 100, okay. So some number of points, and then you put edges between nearest neighbors. You see that some points, multiple points can have a single point as a nearest neighbor. There are possibly some points which could have, there are at least some with a degree 3 also this point. Okay, so apart from its nearest neighbor, 2 other points find this as a nearest neighbor. Okay, so this is a instance of a graph of one nearest neighbor graph. So since it's a small one, the long edges are not quite obvious, but they can be quite long edges. Okay, so that's why I say it's not always, edges need not be bounded in length. Edges can have some tail distribution, which is exponentially decaying in distance. Okay, so this is a point process, interaction graph. So next object for us is I will use my mark, the notion of a mark. I will take my mark to be an initial state of my particle system. Okay, so you give me a mark, each one has a mark, and that mark I assume is say real value, and it will be assumed to the initial state at time 0. And typically we will assume constant or IID for simplicity, but it can be moved. So all of this is presented under some simplifying assumptions to make the main kind of results more easy. But broadly we'll assume constant or IID, it's still interesting enough. Okay, so MX is always constant or it's IID. And now there are a few things I need before setting up the question, is that I'll restrict to a window of volume n. I mean, this is just some centered box of volume n. I will restrict my point process to this always, Pn. And my graph, I will define now on this Pn, on this finite set of points, so it's nicer. And question we are going to ask is that I'm going to have some evolution. Okay, I will make this now more precise in the next, give examples of what kind of evolution I can allow. Is that at time 0, I'm given all these things as input. And based on this graph, this point process and this initial state, the system evolves up to some capital time t, fixed, but some finite fixed time t. I evolve it up to some fixed time t. Okay? Let the system run. And then I want to know the asymptotics for the sum of at time t. We will ask something more complicated functions of this are also allowed. Okay? But for simplicity, let's say I want to know the asymptotics of the sum of states at time t. Okay? So even if m of x0 were IID, this evolution and all these interaction graph dependence can make this object quite highly dependent. Okay, so it's not a sum of independent or anything, and there is a strong dependence here. Of course, we are going to make it asymptotically independent, and that's how we are going to prove various limit theorems. But nevertheless, want to make things a bit more precise. What can be allowed and what is not allowed. Okay, so let's look at examples to make this more clear. Okay, first more is cooperative sequential adsorption, CSA. So again, I take a point process, Poisson or Genebre, I truncate it. I look at a graph, a k nearest neighbor graph. So these two things I'll keep fixed so that in these two things, I can illustrate everything with this simple setup. Okay, and now initial one, I just take a simple particle system which takes only 2 values. Let's say just 0 and 1. The initially everything is 0 or everything is IID 0, 1. and 0 means to me unoccupied, 1 means occupied. Okay. And what is happening? At every site, there is a unit rate Poisson clock. Whenever the clock ticks at some x, and x is unoccupied, it looks at all the neighbors, and based on the state of the neighbors and their locations, it decides whether it should get occupied or not. Okay. So the transition is always from 0 to 1, depending on all the neighboring points, okay, and their states. Okay, it's also the relative distances matter, not just the states, but also the location can be encoded into the evolution. Okay. A very simple example, which is still popular, is called the random sequential absorption, RSA, which is that if there are no occupied neighbors, the site will get occupied with probability 1. Okay, so there is nothing to decide. You look at all your neighbors, there is nobody occupied, definitely occupied. 0 goes to 1 with probability 1 if there is no neighboring 1. Okay, everybody around is 0, 0 goes to 1. Okay, and again, m of x comma t is the state of site x at time t. Okay, because every site there is a clock ticking and it keeps evolving in continuous time. At time t, I will look at the state of site x. I call it m of x comma t. And now, a statistic that we would like to look at, for example, is the number of occupied sites when I stop at some time capital T. I stop at a time capital T, I will ask what is the number of occupied sites at this time capital time. I look also for sites which are occupied for, let's say, half the time, maybe. Okay, at least half the time some site is occupied. So this also I can ask. Okay, I can ask all these kind of things. Okay, so just recalling what is the point process. Again, we have a graph, we have initial states, and then things are getting updated according to a Poisson clock at every vertex. And so let us now state the kind of result illustrative of what we have is, firstly, the expected number divided by n. N is the volume, remember, of the number of the expected number of points in Pn is n. So that's the scaling, converges to something which can be explicitly written. I'll come to this, maybe say what is this E0? It's a conditional expectation. Okay. So, but anyway, there's the explicit expression. The next thing, the variance with the same scaling also converges. Important point, we cannot guarantee that the variance is always non-degenerate. It can be 0. It may be degenerate. Okay. And then, but however, if you can guarantee that the variance grows at least polynomially, then we have a center limit theorem. Okay. So this is broadly the kind of results, and we will actually be, I will give one more example, and later the general theorem all will take a very similar flavor. Whenever I mean limit theorems in this talk, it's essentially only these 3 kind of results. That is the expectation asymptotic, a variance asymptotic, and a central limit theorem. Okay. So this is a kind of results we say, that is, you take a point process which has some weak decorrelation property. You take some graph on this point process, which somehow can have long edges, but not too long. And then you start with initial states, which can also be weakly dependent. And you allow a kind of very generic evolution of these initial states. And you look at some function of the system up to some fixed time t. Okay. And this is a statistic of interest. And what we are saying is that, okay, we can prove expectation, variance, and asymptotics, and a central limit theorem for such a kind of system. Okay. Just to make a little more, the same thing a bit more again, to say what more is possible, again, illustrative only, is that let's take the same kind of basic setup, a Poisson or a Genebre point process, a k nearest neighbor graph. Then I again start with IID 01, unoccupied, occupied. This one, what is called the exclusion rule or exclusion process, is that when the clock rings, the site chooses one neighbor uniformly at random and swaps its state. Okay, it's different than before. Whenever the clock rings, you choose a neighbor uniformly at random and swap the state. And what is the difference with the earlier? In the earlier one, whenever the clock rings, only the state of X is changed. But in this, it's not alone the state of X and a neighbor could be changed. Okay, there is change even in the neighborhood. not alone at X, but also in the neighborhood, there is a change. Okay, so this is what is happening in this model. But otherwise, I can ask a very similar kind of question, state at time t, and then I will ask, for example, in this, I will ask that is X occupied for t/2 time. In this, because the total number of ones or zeros are always preserved. There is no change in the mass. The total mass is never changed of ones or zeros because things are just swapping with each other. But nevertheless, this is a little more random quantity, which can depend on not alone the initial state, it can depend on many, many factors. Okay, that what happens, whether a site is occupied for half the time or not. Okay, so this is something we can ask in this kind of framework. Okay, and in what seems more or less like a repetition of an earlier slide is that I've just changed this evolution and everything else remains the same. The evolution part is changed and the statistics is changed to make it a little more interesting, to say that we can also take functions of the whole system. And exactly copying the same theorem as before. Okay, exactly copying the same thing. One can say that, okay, here also we can get a central limit theorem, even though this has a little more complicated evolution than the previous system. The evolution rule is a little more complicated than previous, but nevertheless, this is quite within our thing. Okay. So what more? I don't want to keep repeating more and more such examples. So just let me give a quick kind of thing that what else is possible. You can take a whole host of pure jump processes. They are very well known ones. Since we did it a lot during COVID, we of course handle epidemic spread. Then you do it various other models, and even discrete time is okay. All this is quite possible. And as a comment on the literature, what is different is that there are some CLTs in the literature, mostly restricted to lattices and transitive graphs. And the state space cannot be polished. Often they need assumption on finite state spaces or so. And also the evolution rule needs to preserve some FKG or some monotonicity property. Okay, it's not a very generic FKG, generic evolution rule, but it needs to have some monotonicity. And this you can find in Holly and Strouk going back, and there was some in between, and more updated version is Dukan and Lang. Okay? Yeah. And if somebody knows something in between, I'd be very happy to know. I've been digging up something more here and there are some comments, but I'm still trying to look where else there can be something. But a more paper that actually inspired us or motivated us was a more recent paper of Penrose, where he considers a Poisson point process. Okay, so and bounded range graphs, you cannot allow a k nearest neighbor graph is not allowed here. It has to have edge length should be bounded, and the initial state should be IID. So Penrose requires all these three restrictions. Okay, and our one thing was to relax all the three. Okay, this is something, as I explained in a particular models, we are allowing relaxation of all the three. Sorry. Okay. And in fact, I mean, 6 months ago, we thought the paper was really complete and everything. And then we suddenly started thinking whether pure jump process is the real restriction. Can we go to something like non-jump process? It's something I cannot describe in the talk quickly. But here is a model that we do handle. We can, if it leads you to wonder, it's very specific to particle system. The techniques are more amenable that at every vertex, you can allow a diffusion, taking values in RL, and the drift and the diffusion coefficients will depend on the neighbors now. Instead of the jumps being depending on the neighbors, we'll allow the drift and diffusion coefficients to depend on neighbors. And this was something that was motivated by a paper of Kavita with Daniel Lacker and Wu. And they use local weak convergence and they can get expectation asymptotics. Okay, they do it under a framework of local weak convergence, and we have been managed to do it for more point process and also prove central limit theorem and variance asymptotics. Okay. So this is a kind of illustrative of the kind of applications and with the kind of theorem. And so with this, I would really now start to move to the general framework, because I still have to take, say, for example, I'm saying that we are relaxing the Poisson assumption. We are relaxing the initial state assumption and the things about the interaction graph. So I want to give some idea of what is the nature of this decorrelation or asymptotic decorrelation or this weak independence. That's the key. Of course, everything you would believe that weakly independent point process with weakly independent initial state and weakly independent interaction graph should satisfy a central limit theorem. Well, this is of course a heuristic, but I would like to make it more clear what is the kind of weak dependence notion that we use. Okay, and that is really the main kind of important thing. Okay, so again, point process, stationary point process, and an important object for point process for us to make precise the notion of weak dependence is this thing called correlation function, which is the probability density that P contains a fixed K points. This is of course not a well-defined a priori because this probability is actually 0. Okay, so you make it a bit more in terms of it's a density. So there are two ways to write this in density. One is I write expected number of points product over disjoint sets. P of Bi is number of points, and it's just I take product of this over disjoint sets. If this has a density that with respect to the product Lebesgue measure, that's called the K point correlation. There's also a more nicer functional form which is more useful. That is, we look at expectation, sum of all distinct K tuples, function applied to that. If I'm saying that assume this can be written in this form, for many point processes this is true. You can write it as an integral of f with respect to some function. That function is called the K point correlation. This is effectively the probability density that there are K points at x1 to xk. Okay, so this is a formal way of formalizing it, which will be important in next slide also and later. And again, mark point process, we will come. I will need also some kind of correlation or decorrelation for mark point process. I'll take it to be MIs. Again, marks and polish pace, everything works on this way. Okay. So this is the next important notion to formalize decorrelation. So K point correlation I have. The next thing I need is a very important concept in dealing with things which are beyond Poisson point process, is what is called PAM expectation. This is a conditional expectation given that P contains those fixed K points. It's a conditional expectation. Again, this is your conditioning on an event of measure 0. So this is not quite clear. How do you make sense of it? And here is a very useful formula, one may say, Campbell-Little-Mekker, and also what defines the conditional expectation. Way of defining the conditional expectation is that I look expectation, sum of a function of K distinct tuples and the point process. It's now not alone a sum of function of K tuples, but it's also a function of K tuples and the remaining points. And this, if I can write it with respect to the correlation function as something, that something is what defines your conditional expectation. Okay, this is nothing but conditional on these K points belonging to the point process. What is F? Okay. Okay. And what makes Poisson very easy in this kind of thing is that this conditional expectation for Poisson is very simple. It's just a usual expectation with those K points added. It's just because Poisson has this strong independent structure, you know, telling me some points of Poisson points in some region doesn't reveal me anything outside the region, which means that if you tell me these K points belong to the Poisson point process, it's as good as just put those K points and take an independent Poisson point process. That's it. So Poisson has this very simple structure. The conditional expectation becomes very simply a usual expectation with these extra points. So that makes it very easy to study Poisson point process in general. But in other cases, this is not always easy to understand this conditional expectation. And this is the kind of thing that when we want to understand weak dependence or weak correlation, everything is based upon how we want to put an assumption here. Okay, this is exactly what we are looking out for. Okay, so now let's really come to the main definition of correlation, decorrelation, and so on. Is that we will say a point process satisfies fast mixing of correlations if you give me two groups of points which are distance s apart. The d here is the minimal distance between the two collections. Okay, the shortest pair of points, the closest pair of points, that defines s. I have a group of p points, a group of q points. Okay, and now what do I look? I look at the p plus q correlation. I look at the p plus q correlation. I split it as a product. of P and Q correlations, that difference should be a constant times a stretched exponential factor. There is a constant and then a stretched exponential factor. Okay. And that constant, I'm allowing it to grow, forget everything, at most k factorial. You can simply think it's growing at most smaller than k factorial, a little smaller than k factorial. So it's a very loose constant to compensate that things can depend and phi of s. Okay. So indeed, this constant is important. If with this constant, there are many examples, it's easy to prove this, but else it's a bit difficult. There is some difference between many earlier works. I mean, kind of weak dependence needed some kind of sigma algebra becomes a product sigma algebra. And if you want something like that, the constants need to be much well controlled. This is sort of weaker than that. Okay, I'm not going to prove, but it's not Poisson clearly, this is 0. And thanks to Shubro, I guess some of you know what is the stationary alpha determinantal. And he had a kernel. The kernel needs to be fast decaying. That is, here for me, fast means faster than any polynomial, stretched exponential typically. Okay, any stretched exponential. And Genebre is one example which has exponential. Stretched exponential is okay. Then there are some Gibbs point process. Then if you have attended Benedict's talk, you will have seen some of the Cox point process also satisfies this condition. So there are many point processes that satisfy. This is a very robust kind of condition in the sense that if you take 2 point processes that satisfy this condition and independently superimpose them, you will still have this property. Okay, the kind of thing is that this doesn't depend very much on the structure, but it is a bit more robust. You can perturb things and still get this property. Okay, now let's go to a bit more than decorrelation of just point process or fast mixing of correlation of point process. Okay, we will put marks, consider a mark point process. What does it mean to say a mark point process satisfies fast mixing of correlations? Again, the same thing, we'll have a P plus Q split into 2 groups. This is a bit more complicated. Let's parse it. What am I doing? I take 2 functions which are bounded. I look at the conditional expectation times the correlation and then split it as a product. It is exactly the same structure, but the conditional expectation, okay, I'm taking the conditional expectation, given these P plus Q points belong to the point process, I'm looking at the expectation of function operated on those marks. And I want them to split as a product now. Okay. I want them to split as a product. And then I'm saying still the same kind of structure holds. I can split this factor as a product. Okay. So I'll let you to just glance at it for a minute. It's not. Okay. So this is a notion of fast mixing of correlations. Okay. And this is a fast mixing of correlations of just a point process. This is a mark point process, which allows us to go beyond just IID marks. Okay. Okay. Now, what is all this good for? Let's start with some basic result that tells why is this important notion. Okay. There are many examples of fast mixing of correlations, a point process. What I will just hide and not focus so much on is that there are also point process with mark point process with fast mixing of correlations. For example, IID is trivial, but you can go a bit more than IID, like local dependence and so on is feasible. Okay, we will see maybe some hints of it later. But now, given all this, suppose you give me a mark point process with fast mixing of correlations, what can we do? So here is a theorem, a kind of an umbrella theorem that helps us to handle many things. Is that take the marks to be real valued. You have a stationary mark point process with real valued marks, and it satisfies fast mixing of correlations. And importantly, I weaken this condition from all bounded functions to bounded one Lipschitz functions. So let me just go back a bit. I needed here all bounded functions. I'm saying that I can even weaken it. Make it all bounded and one Lipschitz functions here. Okay, which is a bit more weaker class. And then assume some moments. So in general, I won't focus on the moment condition. So we will be very loose on the moments. We need all kind of moments, okay, all possible moments. So I'll take all possible moments, and then I look at the sum of the marks. Remember, these are not independent. They have some very, very crude dependence capture in terms of the fast mixing. And all we are saying is if the variance grows polynomially, you have a central limit theorem. Okay. So this is what is the result, which is, okay, for some of those of you would have seen, we are not going to claim that this is a really new kind of this was not kind of there before. There were Cumulant method. It uses Cumulant method CLT. For those who attended Shubro's talk, these were the polynomial things in the characteristic function, Cumulant method, and essentially Marcinkiewicz theorem. It uses a form of Marcinkiewicz theorem. And what we prove is extend this in generality of linear statistics of purely atomic measures. Okay, not alone this, but we look at functions of this measure. Okay, and there were precursors for point process, special cases, and many earlier works. And this is kind of makes it more easier, and also it clarifies a few things and makes it more easy to apply in some cases. Okay, more general than many of them were restricted to just point process in which m of x is equal to 1. And the point is m of x equal to 1 was many of the works, and we are allowing mx to be some atomic thing is the main point here. Okay. Okay, with this in hand, what it tells is that somehow if I can find mark point process with fast mixing of correlations, I get a central limit theorem. So now I'll switch my focus. How do you get such examples of p double tilde or p tilde? Okay, so my entire thing is now narrowed down to finding point process with fast mixing of correlations or p tilde. Okay, I want to find examples of p tilde. I know how to get point process with fast mixing of correlations, but I want a mark point process. How do I do that? Okay, here is a procedure. Why I say it's a bit robust and what helps us. Is that okay? Which seems a bit odd, is I will actually start with something that satisfies this maybe. Maybe just assume IID. Maybe take IID or something which satisfies this already. And then what do? Is that we will assign a score to every point based on the point and all its neighbors. Okay, neighbors, it could depend on a large number of points, but in principle, neighboring points and marks in a crude way. And for example, in the interacting particle system, what did we do? Is that my initial state was m of x0, but after the system evolved at time t, you not alone depend on your site, your location or anything, but the evolution depends on everything around. So potentially it's a function of not alone the initial state or the location, but all the neighboring points. Okay, so it is determined by the initial state m and other initial states, other points. Okay, so this is the kind of simple example to keep in mind, that you have a function that takes as an input the point and its mark, and also it looks at all the other marks, all the other labels, and generates a value. I call it xi. It's a score. The score depends on everything around. Now, what can I do with the score? Is that I can think of it as a new mark point process. I just replace the old mark by the new mark, and it gives me a new mark point process called p prime. Okay. And here is the really key thing to our approach, or I'm not going to make this as a very precise theorem, but I'll clarify, is that if the original point process satisfies fast mixing of correlations with respect to bounded functions, next thing I'm going to say soon, there is the score function cannot be anything. You expect it to satisfy some localization. I'll make this precise next. It's the final piece of puzzle that is missing. Is if this satisfies some localization, and forget moment conditions, some moment conditions have to be there. What do we get is that this new mark point process satisfies joint fast mixing of correlations. Now with not all bounded functions, but bounded one Lipschitz. This is a penalty I pay for taking a localization condition, which is very weak. Okay. So initial point process could have had even IID, but even if you take IID states, a Poisson point process, everything, after running, you have some kind of dependence. Okay. And then what we are saying is that this new kind of score, which is dependently generated based on all the existing points and their states, also has this mixing of correlations property, but with a smaller class of functions. Okay. So, and this is, I'm not going to say how we prove it, but this is, I mean, in most of the things, even for a Poisson point process, this was the missing piece in many, many examples. Okay. And we prove it using what's called a factorial moment expansion. It's a kind of Taylor series expansion for functions of point process. This was in thesis of Bartek, PhD thesis of Bartek, and this particular version is due to Bartek, Elie, Merzbach, and Volker-Schmidt. Okay. And then now once you have this, like use the result from the previous slide, and you get a central limit theorem for sum of scores. The moment I know that my mark point process has this sparse mixing of correlations with respect to one Lipschitz functions, I can apply this umbrella master central limit theorem to say that the sum has to satisfy central limit theorem. So this is just, I mean, this part is more classical. Okay. So this is really the crux of our approach, is that we start with some simple point process. I mean, a point process which has a fast mixing of correlation, but this could be quite simple. Okay, you may sometimes maybe it's not easy to generate a one with a complicated, but you could assume even IID or something like that. And then using this, you generate a further new mark, which is more complicated. And what we are giving are some conditions on the way you generate this new mark and the original point process that ensures this asymptotic decorrelation is preserved. Okay. Preserved, you have to be a bit careful, bounded and bounded one Lipschitz. There is a small difference. Okay. But nevertheless, this bounded one Lipschitz is good enough to get a central limit theorem. Of course, in this entire piece, what is missing is that I said, okay, we have clarified what should be the mixing of correlations of P tilde, what do we mean by that? And then moment conditions, as I said, I'm not going to say, but this piece is missing. Okay. So of course, unless I say xi, it's not clear that why, what does it mean by saying xi? There are examples you would have seen. What we want to say is what kind of examples are this is allowed. So this is the last part of the talk where I will focus on this stabilization or localization condition of xi. Okay. Which again is independent in not just proving a central limit theorem, but it's useful in proving various other limit theorems as well. Okay. So BL stands for bounded Lipschitz, and you can call it stabilization, localization. So it's again just an independent property of what kind of ways can you generate scores which are locally dependent. What is somewhat a very weak way of doing it. Again, it's like almost every slide, the first line is a mark point process. So every time we start with a mark point process, score function, I'm taking, it takes points, it takes marks, and then gives a score. Now, bounded Lipschitz stabilization for me is give me any p tuple of points and any bounded Lipschitz function f. F is a bounded Lipschitz function, meaning that it's a function bounded by one and it's one Lipschitz. You apply the function under, forget it's a palm expectation or a conditional expectation. You apply the function to the full score and you compare it to the function applied to the restricted score. That is, the score is evaluated on a restricted process. That is, the score doesn't see points beyond a window R. Okay, the score you evaluate on the full point process, you evaluate on a small piece of the point process. And then I'm saying that the difference should decay 2 times a stretched exponential function. The 2 is a universal bound because f is bounded by 1, so we just throw in a constant for good measure. But an important fact, which is not bad, is that you need also some constant that may potentially depend on p. Okay, so this truncation to a neighborhood R costs you some stretched exponential factor is this notion of bounded Lipschitz stabilization. Okay, and evaluated on bounded Lipschitz functions. Okay. This is something we haven't seen earlier in the literature, and this is something that's actually, like I said, the last few months have been about trying to see if everything works under this. Seems somewhat nice, but and seems to be so good. Okay. The classical notion of stabilization or so in most of the earlier problems was this notion. What is called strong stabilization is that is not in terms of Lipschitz function, it's actual equality. That the score after some point R is actually equal. That if you tell me all the values of the point process and marks inside ball of R, it's equal. So you can clearly see that this is much stronger than this. Okay, this is something weak and this is strong. So this is a more classical notion you can find in the literature. There are tons of limit theorems under this assumption. And there is some bits to be said. Of course, clearly strong implies BL stabilization. Very simply, if it's equal, it's okay. So this is something that actually enables us to prove even like continuous time, like diffusions really necessitated this notion. Examples, again, in sort of interest of time or so, what I'll say is that, as I said, strong stabilization is classical in literature, so there are many examples. So bounded, if you take a point process that depends where xi is actually, I can truncate it and say that look only at a ball of radius r. This is clearly strongly stabilizing. I can force my score function to look only at a fixed neighborhood. This will be strongly stabilizing for sure. Okay. I can force my score to look only at a fixed neighborhood, then I don't have any problem. But things like distance to the k nearest neighbor is strongly stabilizing on a Genet-Bray point process. So important in all these, the p tilde matters. A score function could strongly stabilize or BL stabilize on one point process, but not on the other. This is quite possible. So for example, that's why I say that distance to the k nearest neighbor, volume of Voronoi cell, these are all strongly stabilizing with respect to Poisson, Genet-Bray, and I think stationary alpha determinantal as well. Some certain kernel assumptions you can prove more. And you have to, this needs a bit of checking, but it doesn't require too much in these examples. Okay, it's possible to check these kind of conditions. Example of BL stabilization is an example I've always bypassed, not said so much, is system of interacting diffusions. In case of diffusions, there is always an effect from very far away points, but the effect is very small. So it will never be equal because the diffusion can interact with a very far away point, but the effect is negligible. That comes up in BL, but it can never be completely equal. This is the point. That's why this BL stabilization is better than strong. Okay, now let's recap the overview. Now everything in the piece I've said, okay, we start with the mark point process. I give a score function. Then all we are saying is we get a new mark point process. Now everything here is clarified. We start with the fast mixing of correlations. We saw it's some way of saying that things decorrelate. And then, like we saw, there is a precise condition of localization, which is not too hard. It's not too hard to state it. Some technicalities are there. You need to take some supremum here and there over some various truncations and all that. But okay, this is the broad way of defining it. And then given all that, you get a new point process with fast mixing, and then you get a central limit theorem. So this is a kind of general approach that we do. Okay. Right. So what are the limit theorems? Like I said, you can also derive expectation variance asymptotics. As you would expect, these do not need the full generality of that kind of assumptions. You can weaken up things. You don't need all moments. You can do with first, second moments like that. So you can weaken up things. Let's discuss the specific examples I said. One, in continuum interacting particle system, we can verify actually strong stabilization itself via a suitable graphical. So there is really one kind of trick you would expect in any interacting particle system is this graphical construction. You just follow the graphical construction correctly, but you need to take care of all the dependencies along the way due to the point process, due to the graph, due to the evolution. It's a lot of Campbell-Little-Maker formulas applied correctly and done more carefully. You can ensure that everything ensures strong stabilization of the score function. Okay, so this is really the I would say the trust of thing that motivated us to really even abstract out the general theorems was this example. At one level, this is a key example that it didn't seem to be under usual geometric central limit theorems. Okay, and then you can deduce central limit theorem expectation invariance asymptotics. Okay, the system of interacting diffusions is now where actually you end up using this BL stabilization. You cannot use strong stabilization, you need BL stabilization. Okay, because the diffusions, there is always, no matter how far you go out, there is a negligible effect, and this goes via, it's an approach from Lacker, Ramanan, and Wu using a lot of standard techniques in interacting diffusions. Okay, the points I would make, even if you take P is Poisson, okay, the one natural thing is if P is Poisson, is all this known, is the baby kind of question to check. There's a lot of literature on Poisson. If P is Poisson, is everything clear? Well, not quite. This kind of stabilization in this generality wasn't shown by Penrose or others. They needed bounded interaction, like I said, IID, initial states, and all kind of things. But this careful analysis of graphical construction that enabled us, that provides this basic kind of stabilization, that was new. And then from there onwards, you can use anything else. You don't need the stimulant method. You can do various other things, and people have done, there's a lot of these gentlemen have done various works in which you can plug in the moment you have the stabilization. Okay, so this is the kind of thing I would emphasize. First, you need to show some stabilization, and then you try to use stabilization to prove some asymptotic independence and get a CLT. And there are other examples we try to sketch in the paper, and hopefully in a few, let's say in a few months, it should be up. But we are happy to share the draft if anyone is interested. Or the slides are, as I said, on my website, and hopefully also on ICTS website. And here are some papers that helped us, some people, and some organizations that helped me. Thanks a lot.
Any questions?
Okay. So not always, but the particular like RSA model or some CSA models where there's some monotonicity, we can take T even to be infinity. But it's not in general true. Okay. So this is not, we have some quantitative possibilities, but it's not clear, is it interesting or is that the rate we allow? We don't say it explicitly, but some of the bounds we derive can be quantified a bit carefully. But if there is a kind of monotonicity and something is nicer in the evolution, you can let T to be infinity also.
Do you have examples where the growth of the variance is not, okay, first of all, not polynomial, but even not volume order? Because your theorem had the growth of the variance in it.
Yeah, so in general, well, even in this kind of cases, not except some trivial things, we have not found a way to verify this always. Okay. So with the score function, we actually don't have a example of, we can show that there are examples. Suppose you look at, instead of P tilde n, if you forget the n, if it's P tilde itself. In this case, it's ongoing work with Manjunath Krishnapur, is that we can get arbitrary low polynomial. But this log, we haven't found, except, or log or constant is except like one-dimensional point process where it's already known. Some determinantal point process or smooth functions satisfy that. To take some smooth statistics, there are examples, but nothing new we have. This is still unsatisfactory.
Are there other questions?
I think I missed this, but at what point are you using a polynomially growing variance?
So when you take cumulants of this, when you take higher and higher cumulants, you can show that the numerator of the cumulant will grow at most like n. Our fast mixing condition will ensure that this cumulant of the numerator will grow at most of n. And then this will just scale up. So the kth cumulant will be variance to the power k by 2. And if you have some polynomial growth and the numerator is at most n, so you can show for large enough cumulants will vanish. And a version of Marcinkiewicz theorem will tell you that it becomes a finite polynomial in the limit.
So if
Okay.
it's like a logarithmic variance, you won't.
Because the bound here we have is n. It's always n, the volume of the region. But of course, in a very specific example, if you ask, you can try to control the cumulant better.
Oh, so it won't.
So I think this has been done in, maybe I think it's in, I don't know if it's in Shoshnikov's survey on determinantal or somewhere, or some other paper. I think it's possible, but I do not know explicitly. I'm just trying to think of top of my head. But yeah, if you control the cumulants better, you can allow lower growth of variance. But it will need often very, very specific structure. Because in this full generality, we are allowing also for Poisson. That automatically will ensure that in many, many cases, that gives the worst possible kind of growth. Okay, no cancellations will happen.
Leave other questions to the break and we'll thank Yogesh again.